Hi AP gang, time for 3-5 derivatives of the trig functions. Now many functions that we like to know about, as you can see, are periodic. Periodic meaning that the same cycle repeats over and over again. I've given some examples here. Here's the heart rhythm one. And oftentimes it's kind of nice to know a rate of change of these periodic functions, as in many other things. So that's why we will like to find derivatives of them. Alright, here's the most basic one that you'll end up memorizing, I'm sure. This says that the derivative of sine equals cosine. And we're going to do something that we don't often do. You probably would do this a little bit more in an actual college class, and we'll do it sometimes, but not often. We're going to actually try to prove that this is true, or derive this. So here we go. Derivative of sine is cosine. So let's just say that we had our derivative, and of course we're going to have to use our limit definition to do this. And remember, we used to say the f of x plus h. Well, in this case then it's going to be the sine of x plus h. My writing is not too good here. Minus the original function, which is the sine of x, and again all of that over h. Now we have to remember here, and those of you who have been away from pre-calc for a while, this might be a little foreign, but you might remember our little chant that we did, our cheer, when we had these trig identities. And sure enough, this is one of these addition formulas. Remember, we had our sine, cosine, cosine, sine, cosine, cosine, sine, sine. Sorry, I can't do the arm motions for you here on video. But here's our sine addition formula. And so you may recall then, as we just chanted, that expanding this out would be the sine of x times the cosine of h plus the cosine of x times the sine of h. That's from chapter 7 in our pre-calc book. And then we're going to subtract our original sine function here again, and all of that is going to be over h. Now this might look like kind of a bunch of mishmash stuff, but notice what we do have here is we have a couple of common factors. We have a sine of x here and a sine of x here. So what I can basically do then is factor out that sine of x. So I'll do that here. So we have the sine of x, and then I'm going to left here with the cosine of h, and then minus 1. That comes from this sine of x here. If I distribute this, I'll get all of this and all of this. And meanwhile, what I have left then is plus cosine of x sine of h. All of that. And of course, I still have this over h. Now, one property of limits is that when we have products and things like that, we can kind of separate it out into various parts. So what I'm going to do here is I'm going to separate these. So this is going to be the limit of the sine of x times the limit, again as h approaches 0, of this other part, cosine of h minus 1 over h. Okay, plus, because I have a plus sign here, the limit, all of these are as h approaches 0, of the cosine of x, times the limit, again as h approaches 0, of the sine of h over h. Again, we're splitting this into basically two fractions, so this would be one fraction, this would be another fraction, and I can have just h under one of those through some algebraic means. We can talk about this in class a little bit more if we need to. Alright, let's just finish this out and see what we get. So, what's the limit of sine of x as h approaches 0? Well, there's no h at all in this expression, so that's just not going to change at all. That's going to be just the sine of x. Now, what about my second one here? Well, if we think about our trig functions here, again, this is as h approaches 0. What is the cosine of 0? You may have to refer back to your circle chart or something like that perhaps, but the cosine of 0 is actually I'm going to change pen colors here for a little bit. The cosine of 0, remember, is actually 1. And so in this case, we'd have 1 minus 1. We're not going to quite put 0 in place of the denominator because it'll never get there. And actually, my answer then will end up to be 0 here. 0 over anything is 0. Meanwhile, second part here, again, this is like the first part. The limit of cosine of x as h approaches 0. H has nothing to do with the cosine of x, and so that's going to be just plain the cosine of x. And the second part here, the sine of h over h, you might recall this was one of the things we had you memorize in the limit unit. This is a fairly famous one, the sine of h over h as h approaches 0, and that's actually going to be 1. You could graph that to verify that perhaps. Anyway, look at what ends up to be here. The sine of x times 0, of course, is 0, and I end up to be just the cosine of x. And I could put my little check mark there to see that I have verified this derivative. So, might be a little confusing, but hopefully that helped to understand a little bit more where that came from. Alright, let's actually look at some more of these. We're not going to derive any more of these formulas, but make sure to write each of these down. They're in your pink spark chart as well, but it'd be good to have these down in your notebook. Again, these are just all derivatives. The derivative of cosine is negative sine, and here's tangent and cotangent, their derivatives, and secant and cosecant. So you may want to pause this video just a little bit so you can write down all those particular derivatives. Now we're going to actually get to working on some of these problems here. So let's take a look at these. We're going to find the derivative of each of these. So on our first one, y equals 2 sine x tangent x. So we just take each one separately because they are separated by a subtraction sign. I still need the 2 here, and the derivative of sine is cosine, so I can just write that down. So 2 cosine x. And the derivative of tangent, as you wrote down just recently, was secant squared x. And that's all there is to that one. So that was a pretty easy one. Now, next one will prove to be a little tougher, I think, because it looks like we have a little quotient rule going on here, don't we? So if I'm doing the derivative of this one, so it's our HODI high. So here's our ho, or our low one here, 1 plus sine of x, times the derivative of the first one, and we remember that the derivative of cosine now is negative sine. Kind of running out of room here. And then minus high d ho. So high is just the cosine of x. And the derivative of the low, or the whole one there, 1 plus sine, well, 1 won't have a derivative, but of course the derivative of sine is cosine. So here's another cosine of x here. Apologize for not leaving too much room here. And of course that's going to all be over 1 plus sine of x squared, like that. Alright, so then trying to simplify that a bit, I'm going to actually have to do a little distributing here, right, with this negative sine x. So when I do that, I'm going to have negative sine of x minus sine squared x, right? And then minus cosine times cosine is cosine squared x, like that. And my denominator, I'm just going to leave it in this factored form like this, 1 plus sine of x squared for now anyway. Now look at what happens on top. And here's where, again, you have to bring your little trigonometric knowledge into play here. Would you agree that I can write it like this? I'm not going to change my first expression at all. But if I put a minus sign and then I put parentheses next, notice I'm going to have sine squared plus cosine squared, like that. Again, all over that same denominator, 1 plus sine x squared. And especially those of you who are just coming from pre-calc, you might remember that sine squared plus cosine squared is 1. 1. So I'm really going to have negative sine x minus 1 and 1 plus sine x squared there. Now you could leave it like that perhaps, although we can do just a little bit more with this, I think. Again, just a little trick on the numerator there. I could write that as negative, and then sine x plus 1. Negative sign out in front, remember, will change each of the values to the opposite. And then 1 plus sine x squared, I still have that in the denominator. Now you probably recognize that both this numerator and denominator are the same. This one in the denominator is squared though. But I can cancel out one of these guys. And so I end up with a final answer of negative 1 over 1 plus the sine of x. So that's a fair amount of work, and you can get bogged down on ones like this. But again, just take your time, slow down, and use your derivative rules and some good solid algebra techniques, and you can get these buggers. But notice the difference in work between the first one and second one here. Alright, we might not get through this one before I might just get started on this and maybe try to finish this in class perhaps. Find an equation of the line normal to the graph of y equals the tangent of x over x at x equals pi over 4. Now remember that word normal, that means what? Perpendicular. Perpendicular. So we know that we've done some tangent lines, and the normal line is actually perpendicular to the tangent line. So let's just get started on this one, and I might stop so we can kind of finish in class tomorrow, but let's just see how we might get started on that. Well, of course, if we're trying to come up with an equation of a line, we want to know what the slope is, and typically then our slope a lot of times of tangent lines would be the same as the derivative. But normal is a little bit different, and yet it is related. In fact, if we find the slope or the derivative of this, we'll be able to find that, and then we want that opposite reciprocal in order to get our perpendicular line here. So let's at least start with finding the derivative, and then that might be about all we'll have time to do today. Alright, so if I want to find the derivative of this, again, notice that in a sense this is one of our quotient rules here. So I have to take, this is tangent of x over x, so ho d high, so my ho is just x. The derivative of tangent is secant squared. Okay, so that's my ho d high minus high d ho, so that's tangent of x. And the derivative of just plain x in the denominator is 1. So that's not too bad. And then my denominator there is just going to be x squared. Alright, so that's actually not too bad. That looks a little nasty, but that's the deal there. Now the question is, I need to find a specific value, so I'm going to put pi over 4 in place of x. So here's where it gets just a little bit hairy. So I put pi over 4 there in place of that x. Now your circle chart, which will distribute what is the secant of pi over 4. Well, secant, 1 over cosine. You might recall that pi over 4 is 45 degrees. Cosine of 45 degrees is the square root of 2 over 2. But then 1 over that, well, that's actually going to be the reciprocal of the square root of 2 over 2 will end up to be just plain the square root of 2. So we got the square root of 2 squared, and of course the tangent of 45, you may remember, is 1. And then I still have to put that pi over 4 in place of this x, so I get pi over 4 squared. Now, can I simplify that, because that looks like kind of a bear cat? Well, I think so. You might recognize that this, the square root of 2 squared, is just going to be 2, and 2 times pi over 4 would be 2 pi over 4, which would just be pi over 2, I think, right? Minus 1. And meanwhile, then we have this pi over 4 squared, which I suppose I could simplify that a bit to get pi squared over 16. Again, I'm just doing all this just to find the slope. And again, we might stop there for today. Pi over 2 minus 1. Remember, I could write that, if I'm writing that as one fraction, as pi minus 2 over 2. That was writing this as 2 over 2. And then if I'm dividing, it's like multiplying by the reciprocal, so I could multiply it by 16 over pi squared, like that. So I'm going to end up with my, looks like I'm going to have 8 times pi over 2, doing a little canceling there, over pi squared. And I could write that even then as 8 pi minus 16 over pi squared. I think I'm going to stop right there. We'll continue on this problem tomorrow in class. Thanks for hanging in there. Tough stuff as we learn about these trig derivatives. Bye now.